Hello everyone, my name is Gabby Myers. I'm a PhD student in Ag and Biosystems Engineering. My major professors are Raj Raman and Dan Anderson, and my other committee members are Amy Kalita, Ken Moore, and Bobby Martins. Today I'm going to be talking about my dissertation topic, which is evaluating an integrated perennial ground cover and anaerobic digestion system. When you think of Iowa, you might think of the highly productive agricultural systems we have in place here. Iowa's farmers produce more corn than any other state and more than most other countries. Iowa is also the leading hog producer in the country, with far more pigs inhabiting the state than people. These systems provide the world with food, feed, and fuel, but they are not without their challenges. In a traditional corn and soybean rotation, the field is left bare for a portion of the year. The lack of plant life and root mass leaves the soil vulnerable to erosion and leads to the export of nutrients via runoff and leaching, reducing water quality in Iowa and far beyond. The large number of pigs we have in the state produce a large volume of manure. Properly handling this manure is a challenge for farmers who want to minimize air and water pollution due to the manure, while also maximizing the recovery of the valuable nutrients it contains. One way farmers deal with manure is through anaerobic digestion. Anaerobic digestion is the process by which microbes break down organic material to produce biogas, which contains mostly methane and carbon dioxide. Manure can be used as a feedstock for anaerobic digestion, and the captured biogas can then be upgraded to renewable natural gas quality and utilized as a transportation fuel. In addition to manure, using corn stover as a feedstock in anaerobic digestion may increase the digester's productivity. One proposed solution to the bare soil problem is perennial ground cover, or PGC systems. A PGC system provides year-round ground cover in agricultural fields. These systems may reduce soil erosion and nutrient export, as well as possibly allow for increased corn stover removal from fields without the negative soil health drawbacks. The PGC systems being developed are also less complex to manage and less expensive than conventional cover crop systems. In my research, we are looking at a combined system of anaerobic digestion and perennial ground cover. Anaerobic digestion is most often deployed at dairy farms, and the biogas is utilized to create electricity, so less is known about the economics of a swine manure corn stover system that upgrades biogas to renewable natural gas quality. With the perennial ground cover system, the water quality impacts have yet to be fully validated. I have three main research objectives. The first is to validate the water quality impacts of the PGC system through field trials in Nashua. The second is to explore the economics of the swine manure and corn stover co-digestion system. And the third is to evaluate the environmental impacts of that same system. Long term, I hope to provide concrete information to farmers and other stakeholders on the environmental and economic impacts of perennial ground cover adoption. And secondly, I hope to provide an economic model that could be utilized by livestock farmers to determine the best course for anaerobic digester use.
Hey everyone, my name is Alex Cleveringa and I'm a PhD candidate at Iowa State University, majoring in crop production and physiology in the Department of Agronomy. I'm advised by Dr. Fernando Miguez, and today I'm going to be presenting a poster about my preliminary univariate analysis of end-of-season cornstalk nitrate test data. Nitrogen deficiency is the leading limitation on crop yields worldwide. Additionally, it is one of the leading costs farmers incur. It is not only financially expensive, but energy intensive. Approximately 2% of global energy consumption is used to create ammonia to be used as fertilizer. Unfortunately, as expensive as nitrogen fertilizer is, the global nitrogen use efficiency is around 33%. It is estimated that the chance of applying nitrogen fertilizer to an individual field at the economic optimal nitrogen rate, or EONR, the red diamond on the blue line, is only 20%, and the chance that the recommended rate might lead to overfertilization is about 60%. Missing the EONR in either direction has negative consequences. If a producer underapplies nitrogen, that's missed grain yield and income, and overapplying is a waste of money for the producer and harms the environment. The cornstalk nitrate test is done by sampling a specific portion of the cornstalk at the end of the growing season and testing it in a lab for nitrate content. The amount of nitrate in the stem at this time indicates how much nitrate was available to the crop throughout the growing season. The results are then categorized into 4 bins: deficient, marginal, optimal, and excessive. The goal of this study is to identify relationships between soil management variables that lead to better accuracy in making nitrogen application rate predictions at the individual field level. A valuable resource we have at our disposal is a large network of on-farm data. On-farm data has gained viability due to advancements in precision agriculture and the development of simple, accurate measuring tools. Having a network of farmers collect their own data for us to analyze allows for a much larger data set than a research group could collect on their own from standard small plot experiments, and covers a broader range of management practices, soils, climates, and years. We have data from over 4,000 fields across Iowa collected over 12 years. Another benefit of on-farm trials is that farmers are more likely to adopt new practices when they participate in these studies. To guide our thinking, we have created directed acyclic graphs, or DAGs, to think about how these variables are related. These relationships are complex, and diagramming them is a continual process, but some important ones we have identified so far in their effect on CSNT are previous crop, tillage, and fertilizer form. This is a daunting challenge, but the goal is to increase our predictive capabilities from something that looks like the target on the left to the target on the right, where we are more precise with our predictions at the individual field level. Join me at the poster session, and I look forward to discussing my project further with you. Thank you.
Hello everyone, my name is Jarrett Morrison. I am a master's student here at Iowa State in the Department of Civil, Construction, and Environmental Engineering. I'm working with Dr. Lu Liu here on campus, and today I'm going to talk a little bit about our research of enhancing the resilience of Houston's wastewater system under wet weather using emerging technologies. So the study area that we will be looking at is the Houston, Texas area. And in 2017, we observed a hurricane that devastated much of Texas, and specifically the Houston area. As a part of that, we observed many of the wastewater treatment facilities flooding, and as such, they were failing in their conditions and not able to meet our regular standards. And so that's part of the project here, is to use emerging technologies to, one, model what was going on in this flooding event, but also to see if we can enhance the resilience of these emerging technologies. So our objectives are quite simple. Well, we were working with Howard and Rice University on this project, where we used membrane biofilm reactors in order to, one, observe how those emerging technologies can affect a wastewater treatment plant, and also to observe how that looks under wet weather conditions. Our goal in this part of the project, Dr. Lu Liu and I are working on creating a whole system level, where we're modeling the entire wastewater system of Houston, Texas, and using those emerging technologies, biofilm reactors, in order to improve the resilience. That is the goal of what we're trying to do. So overall, what we are expecting to see is a performance curve similar to this, where we have our constituents such as nitrates that we naturally have removed in our wastewater treatment plants. And we'll see that under wet weather conditions, when they were failing, a lot of these wastewater treatment plants were not meeting the appropriate amount of removal. And so we see this dip in removal rates, and then it slowly returns back to normal. What we want to see with implementing these emerging technologies is that we decrease the amount of reduction, decrease that level of dip, and also improve our recovery time. So that way we can measure the resilience of using emerging technologies in this case.
Hi everyone, this is Mutahara. I'm a PhD student at Industrial and Manufacturing Systems Engineering at ISU, and today I'm going to talk about my research, which is supply chain design for chemicals from biomass. CO2 emissions from human activity are causing climate change. And to reduce the carbon footprint, the chemical industry will need to switch to renewable energy and replace petroleum with biomass. So we're going to have greener materials with the help of greener energy. And electrochemistry has shown promise for producing chemicals from biomass. The objective of our project is to understand and address the scientific and technological barriers to an electrochemical process for the distributed manufacturing of high-value monomers and performance advantage polymers from biomass. To do so, we need to design a proper supply chain from the very first part, which is related to biomass cultivation, into the very end part, which is related to demand zones in the market. This is a simple network for our supply chain. In each step, as you can see, we need to define our known parameters and we need to define our decision variables. For example, in cultivation sites, we know about the cultivation cost, harvesting cost, and maximum available lands. And we need to decide about land devoted to cultivation and amount of harvested biomass. So we need to decide about devoted lands for biomass cultivation, the amount of biomass harvested in cultivation sites, the amount of harvested biomass transported from cultivation site to pre-processing facilities, amount of densified biomass transported from pre-processing facility to conversion facilities, and amount of chemicals produced in conversion facilities and transport to demand zones. And also we need to decide about location of each facilities. And our objective here is to minimize the total annual cost, which would categorized into fixed facilities cost, biomass production cost, pre-processing cost, chemical production cost, and transportation costs. Of course, in each step, we will face some constraints which need to be taken into account. For example, in cultivation sites, we need to respect limits on available land and the limit on yield in each time stage, the conservation of biomass, and we should pay attention to the inventory balance at each time stage. Our next step would be formulating a deterministic optimization model and then adding uncertainties in order to make it more realistic, and then finding a solution procedure to find our model.
Use of fertilizers containing high amounts of nitrogen has been crucial in helping farmers increase corn yields and meet the needs of an ever-growing population. Unfortunately, not all of the nitrogen in those fertilizers ever meets its intended target. In order for corn to have its nutrient needs met throughout the growing season, farmers will apply fertilizer early on, long before the crop has a high need for nitrogen. During this lag between application and plant uptake, the nitrogen in those fertilizers is left vulnerable to environmental losses, such as nitrate leaching and nitrous oxide emissions, each with their unique consequences. Nitrogen in leached water can be carcinogenic and can contribute to the degradation of an ecosystem downstream from a given field. Alternatively, when lost as nitrous oxide, the nitrogen from those fertilizers gets transformed into a greenhouse gas, 300 times more potent than carbon dioxide, and with the additional capacity to contribute to ozone destruction. Given these problems and the need for fertilizer, it is imperative to properly understand how much nitrogen from fertilizer succumbs to these environmental losses. In the past, many studies have used traditional field plots to do this. However, there's a problem with using such plots to study nitrogen loss. Traditional field plots are open both on the sides and on the bottom to the surrounding soil, so any water entering the plot can freely escape through these open sides and bottom, taking with it nitrogen we are trying to track. When this happens in our studies, the fertilizer that we apply ends up getting diluted into the surrounding soil, making it difficult to measure its contributions to environmental losses. This is where my research comes in. For my PhD project, I'm using a novel field design you can see in the picture. My research addresses the problems of traditional field plots by harvesting massive blocks of soil and fully enclosing them both on the sides and on the bottom with steel, as you can see in the diagram. To the bottom of every soil block is a single pipe that collects all of the excess water that would normally be lost through the sides and the bottom. By fully enclosing the soil with steel and completely collecting all of this water, I am ensuring that there'll be no sneaky escapes for nitrogen diluting my fertilizer applications. Into every block then, I'm applying a given fertilizer rate that I'm interested in studying and growing corn just as you would any traditional field corn. Except, of course, I'm also taking numerous measurements of nitrate losses and nitrous oxide emissions individually from each block. With these measurements, I'll be able to better understand how much nitrogen in fertilizer succumbs to environmental losses, affecting both our own health and our planet's health. Thank you.
My name is Meyer Bond. I'm a PhD candidate here at Iowa State University in the Department of Agronomy, studying soil morphology and genesis. I'm advised by Dr. Bradley Miller, and today I'm going to be talking about the impacts of soil's input data on maize biomass and yield simulations. Agroecosystem process models are excellent tools for predicting biogeochemical cycling, especially in high production areas like Iowa. And these models help us to inform on-farm management decision makers on methods that will optimize production while maintaining soil quality and mitigating environmental risk. The inherent problem with these models is that they are very sensitive to soil's input data, so we can run into the issue of getting garbage in, garbage out in terms of our simulations. This study investigates the impact of different soils data, i.e. the Soil Survey Geographic Database provided by the Soil Survey staff, versus some site-specific high-resolution digital soil maps that were made for this specific farm. And this study was carried out at the Sustainable Advanced Bioeconomy Research Farm west of Ames here. It's a 28-hectare field and has soils that are part of the Clarion-Nicollet-Webster Soil Association. Maize simulations of biomass and yield were performed with the simulation engine known as AppSim, the Agricultural Production System Simulator. And we focused on the growing season of 2018, looking to evaluate the differences. And the biggest differences that we saw that although the predictions for Surgo versus digital soil mapping had about the same range in terms of variability, it was quite evident that the digital soil map soil input data produced substantially lower above ground biomass and yield predictions. So join me this afternoon as we go into the details and explore this study. Thank you for your time.